Welcome to the deep dive. You know, for the longest time in AI, the thinking was pretty straightforward. Get more data, throw more compute at it, build bigger models, and, well, you get better results. Seemed almost like a law of nature, didn't it?
It really did. That scaling curve was pretty reliable for a while.
But what if? What if giving these incredibly powerful AI models more processing time, more layers to sort of think things through, actually makes them worse?
Uh-huh.
Today, we're diving into something fascinating and honestly really counterintuitive. Researchers are starting to talk about an inverse scaling crisis.
Right?
The basic idea is that sometimes making a model think harder can actually tank its accuracy,
Yeah.
its logic, even its security.
And that's precisely what two very recent research papers are digging into. It's not about saying AI is doomed or anything like that,
Not at all.
but it's a really important reality check. We're looking at findings from Anthropic and also a big collaboration led by Google DeepMind with folks from Princeton and Carnegie Mellon.
And they're basically telling us, hey, maybe hold off on just blindly adding more compute.
Exactly. Time to look under the hood a bit more.
So this is super relevant for you, whether you're actually running LLMs in production, worrying about costs and security, or maybe you're just fascinated by how these neural networks work. Our mission today is to unpack all this evidence, put it in plain language, and figure out why that old mantra, just add compute, can sometimes lead to these, well, pretty surprising failures. Let's get into it.
Okay.
So for ages, the main idea, especially with LLMs, was clear, wasn't it? Dev teams saw compute like marathon runners see water. More is always safer.
Yeah, that assumption came straight from those classic neural scaling laws, the ones that gave us GPT-3 Chinchilla. They showed this nice, smooth improvement. More parameters, more training data, lower loss. Simple.
But sort of anecdotally, users were seeing weird things, right? You'd hear about a chatbot acing some super complex math problem
Yeah.
and then completely failing to count, I don't know, forks on a table. It felt odd.
It did feel odd. And the usual advice was, oh, just, increase the temperature or let it generate for longer, which always felt a bit like...
Like a Band-Aid.
Exactly, like a Band-Aid.
Yeah.
And these new papers, they basically formalize that feeling. They've run controlled experiments, and they show pretty definitively that for some kinds of tasks, performance actually gets worse the more test time reasoning you allow.
Okay, so if more compute isn't always the answer, where's the proof? Anthropic's work seems key here, especially this idea that longer reasoning can actually amplify flaws. What did they find?
Well, their core finding was, and I'm quoting loosely here, extended reasoning can amplify flawed problem-solving strategies.
Amplify flawed strategies.
Yeah.
Okay.
So to test this, they set up 4 different types of tasks. Some were simple, like counting things, but with distracting information thrown in. Others involved regression problems where there were misleading correlations. Then classic logic puzzles, like that zebra puzzle.
Oh, yeah. Who owns the zebra? Who drinks water?
That one. And also AI safety prompts. They really wanted to see, does giving the model more tokens to generate its reasoning actually help, or does it hurt?
And they use big models for this, right? Not just toy examples.
Oh, yeah, absolutely. Claude Sonnet 3.7, Opus 4, DeepSeek R1, Qwen 3, even some of the OpenAI O series models. The heavy hitters.
Across these different models and tasks.
The consistent finding, maybe the alarming one, was that on many of these tasks, accuracy went down when the model was told to think harder by generating more output tokens.
Wow. Okay. That really does challenge the standard approach.
It absolutely does. Now, if we switch over to the Google DeepMind paper, they were looking at it more from a security and robustness angle.
Right.
And their main takeaway is just as striking. They put it very bluntly. Robustness consistently decreases as inference-time computation increases.
Robustness decreases. Okay, that sounds bad, especially for security. And didn't they do something pretty bold with the model's internal thinking?
They did. They deliberately exposed the model's chain of thought. The step-by-step reasoning it generates internally.
No, okay, so they let people see how it was thinking.
Exactly. And then they hit it with prompt injection attacks,
Mm.
trying to sneak in malicious instructions, and also extraction attacks, trying to pull out sensitive information.
And what happened when the thinking was out in the open?
Well, it was pretty worrying. The longer the chain of thought, the more the model thought out loud, the more successful the attackers were.
So showing its work actually made it more vulnerable.
It seems so. It was like every extra reasoning step, every extra token it generated internally was another potential weak point, another piece of rope for the attacker to pull on.
Okay, let's try and make this really concrete. Imagine asking a friend who's super tired late at night, okay, I've got 1 apple, 1 orange, how many fruits?
Right. They'd say 2 and be done with it.
Exactly. But now imagine asking let's say, a very brilliant, but maybe overly analytical data scientist the same question. But first, you bombard them with useless info probability charts, pi digits, some random Python script.
They'd still get to 2 eventually.
But only after writing a mini thesis on Bayesian inference or something.
Right. And it turns out large models can sometimes act like that second friend, overthinking the simple stuff.
And Anthropic actually built a test like this, right? Their apple and orange test, but with added noise.
They did. They took the simple counting task and added distracting information percentages, math symbols, even valid Python code snippets that didn't actually do anything relevant.
It's noise.
Pure noise. And then they let the models generate reasoning steps from 0 extra tokens up to over 4,000. And this really highlights that first theme we're seeing. Distraction inflation.
Okay, so what happened? Did the models get distracted?
Massively. The numbers really tell the story. For that simple fruit counting, Claude Opus 4 with 0 extra reasoning tokens, 99% accurate. Almost perfect.
Makes sense.
But give it 4096 tokens to think. Accuracy drops to about 85%. And DeepSeek R1 went from 96% down to 70%.
Wow, just from adding irrelevant text nearby.
Exactly. The models just couldn't seem to ignore the noise. They started integrating these stray clues, treating distraction as if it were part of the signal, part of the problem to be solved. It dilutes their focus.
And while counting fruit seems basic, you can see how this distraction inflation could cause real problems in bigger systems, right?
Oh, absolutely. Think about any system using argog retrieval, augmented generation, pulling in documents, or systems that need to follow really long, complex instructions. There's a risk that irrelevant bits from those documents or instructions get woven into the reasoning and just derail the whole thing.
Okay, that's distraction. What about the second theme? You mentioned surface heuristic fixation. Anthropic had another test for that.
Yeah, this one involved predicting student grades based on lifestyle factors from a real data set. Things like study hours, sleep hours, stress levels.
And initially, the models got it right.
Initially, using zero-shot prompting, just asking directly the models correctly identified study hours as the most important factor, which matched the actual data.
Okay, logical.
But then, when they increased the reasoning budget, let the models think more about it, something strange happened.
Right.
Many models started shifting their focus. They began prioritizing weaker factors, like sleep hours or stress level, even though these weren't the main drivers in the data. The error rate went up, even while the models often remained highly confident in their flawed reasoning.
So more thinking led them down the wrong path.
It amplified their bias towards things that seemed plausible but weren't actually correct. They fixated on a surface pattern. Though, interestingly, there was a partial fix.
Oh, yeah. What was that?
Using few-shot prompting,
Yeah.
showing the model a couple of correct examples first helped significantly. It seemed to kind of anchor the model back to the important features.
Right, giving it a nudge in the right direction. Okay, so beyond stats, what about pure logic, like those zebra puzzles? That brings us to the third theme. Memory budget overflow. How did models handle those?
Ah, the zebra puzzle. Classic logic grid. You have clues, you have to deduce who lives where, drinks what, owns which pet.
Right, needs careful tracking.
Exactly. And what they found is that as the puzzle gets bigger, more complex, the models naturally try to reason it out step by step, maybe writing down intermediate conclusions. But this overthinking, in a way, taxes their internal memory.
It's too much to keep track of.
Precisely. It's like their working memory gets overloaded. DeepSeek R1, for example, started around 60% accuracy on simpler versions, but plummeted to almost random guessing, near 50%, when it had to generate around 12,000 tokens of reasoning for harder ones. Each step it writes down adds to the context, potentially diluting focus and overwhelming its ability to manage all the variables.
It reminds me of that hiker analogy you mentioned, packing too much stuff in the backpack.
That's a great way to put it. Each item, each reasoning step might seem useful on its own, but load too much cognitive baggage without a way to filter or prioritize, and suddenly the model can't see the path anymore. It's too much to hold, too little filtering. And that connects directly to the fourth theme, security surface growth, which we saw in the DeepMind study.
Right, where exposing the chain of thought made things worse.
Exactly, because every extra token, every intermediate step shown, just creates a larger surface area for an attacker to target.
More places to inject bad instructions or pull out data.
Precisely. Even if the model's final answer looks safe and compliant, an attacker might be able to grab sensitive info or insert a jailbreak command during the reasoning process.
And the data on that was pretty stark, wasn't it?
It was. They had this test with a high-priority instruction mixed with a low-priority malicious one, With only 100 reasoning tokens, a model like Star 114B mostly ignored the bad prompt,
Okay.
but let it run for 16,000 tokens. The same model followed the malicious instruction over 70% of the time.
Whoa, why such a big jump?
The scary part is why. Even when the final output is safe, the model might still generate the unsafe content internally as part of its process. It might think about fulfilling the malicious request before deciding against it. But that internal spill is enough for an attacker script watching the process to grab and exploit.
So transparency, showing the work, can actually backfire badly in security contexts.
It really challenges that default assumption that more transparency is always better. For safety-critical stuff, maybe hiding those intermediate steps isn't just about preventing theft. It might be a necessary shield against hijacking the model's logic mid-thought. Perhaps transparency needs to be graded, selective.
Okay, so let's recap these 4 themes driving these failures when models think too much. We've got distraction inflation,
Where noise gets treated like signal.
surface heuristic fixation,
Where plausible but wrong guesses get reinforced.
memory budget overflow,
Where the model drowns in its own intermediate thoughts.
and security surface growth.
Where every extra thought token is a potential vulnerability.
Taken together, it really feels like these themes explain how we get this inverse scaling, how the helpful scaling laws can flip and suddenly more compute means more trouble.
Exactly. That phrase, bigger isn't always better, isn't just a catchy slogan anymore. It's showing up in the data, in these performance curves. It's something we really have to grapple with now.
So the million-dollar question then, can we fix this? Can we patch this paradox? Are there ways to get the benefits of reasoning without these downsides?
Well, both research groups do offer some potential mitigations. They feel pretty intuitive once you see why things are going wrong.
Like the few-shot prompting you mentioned.
Right. Anthropic showed that giving a few good examples helps combat that heuristic fixation. And DeepMind suggested things like, well, maybe don't expose the full chain of thought in sensitive applications, or put caps on the reasoning budget to limit the attack surface.
So control the exposure, control the budget.
Pretty much. Neither paper claims these are silver bullets, but they strongly hint that future AI architectures need to be smarter about allocating attention, kind of like how a chess engine prunes moves that look unproductive. And one really interesting idea emerging is this concept of adaptive compute.
Adaptive compute. What's that?
Imagine the model having an internal monitor. It looks at how much new, useful information seems to be emerging with each step of reasoning. You could call it entropy gain per token.
Okay.
If the model's confidence isn't really improving, or if it seems like it's just repeating itself or going in circles.
Just spinning its wheels.
Exactly. If it's just spinning its wheels, this controller could step in and say, okay, stop generating now. We've probably got the best answer we're going to get.
So it stops early before it gets into trouble.
Right. Which is not just cheaper and faster, but potentially safer too. Prevents that runaway reasoning. Apparently, OpenAI has experimented with similar ideas, calling it budget forcing. It's not perfect, but it's definitely smarter than just setting an arbitrary huge token limit and hoping for the best.
That actually makes a lot of sense. I heard about an enterprise team that sort of stumbled into this. We called it the voice assistant that learned to shut up.
Oh, yeah.
They had this assistant for setting up devices. Version 1 showed its whole reasoning process in the debug logs. You know, thinking out loud.
One target for phishing, I bet.
Totally. But in version 2, they added a simple switch. After about 5 reasoning steps, it just gave a short, compressed summary justification instead of the whole tree. Attackers couldn't get anything useful, the logs were smaller, and get this, the time it took actual users to onboard their devices dropped by half.
Wow. So less thinking was actually faster and safer.
Yeah. It was
Yeah.
like AI scaling discipline and practice.
Yeah.
Use tokens wisely, not just
Right.
everywhere.
That's a great illustration.
So given all this,
Yeah.
where does AI go from here? Do we scale smarter or maybe scale narrower? What are the paths forward?
That's the big strategic question, isn't it? I think we could see maybe 4 potential paths. 1, we keep scaling up bigger models, bigger context, but we build in much smarter filters. Circuitry designed to ignore trivial noise, detect when the model's drifting off track. Basically, scale smarter.
Makes sense. Path 2?
Path 2 could be scale narrower. Instead of trying to build one model that knows everything, maybe we focus on highly specialized models, experts in specific domains, like those old expert systems, but powered by modern AI techniques.
Domain-specific intelligence.
Yeah.
Okay. Third path, hybrid reasoning. Use the LLM for its strengths, creativity, understanding context, but then have a separate, more rigorous system, maybe a symbolic logic engine or a rule-based checker. Verify the LLM's output, especially for critical steps.
Like a fact checker built in.
Sort of, yeah. Offload the brittle logic. And the fourth path, well, it's maybe less technologically exciting but practical. Human in the loop by default. Especially for tasks requiring really long, complex reasoning, maybe the default is that a human needs to approve it before the compute budget gets spent.
Let people decide when the deep thinking is truly necessary. Right. Which path or combination of paths will wins out? Who knows? But what's clear now is that the question of why do these super smart AIs sometimes fail at simple things isn't just a funny anecdote anymore.
No, it's measured now.
It's measured, it's graphed, it's repeatable. Now you might ask, wait, do the old scaling laws still hold? And the answer is yes. Mostly.
Literally.
They still seem to hold during pre-training. Add more data, more parameters during training, and the models generally get better, loss goes down. The problem, this inverse scaling, really pops up during deployment, at test time, when you specifically ask the model to use more compute to generate longer reasoning chains. That's a different axis, one the old laws didn't really account for.
So we need new ways to measure performance along that reasoning length axis.
Exactly. And it's important to remember that AI progress isn't always a straight line up. Sometimes performance gets better, sometimes it stalls, and sometimes it actually dips before recovering later with even more scale. Researchers call that a U-shaped scaling curve.
A U-shape, so it gets worse before it gets better.
Sometimes, yeah. Think of it like maybe a teenager's growth spurt. There's that awkward phase where coordination is off, things don't quite work right.
Ease buckle.
Right. But then, with more development, more growth, things smooth out again, and they end up more capable than before. Some AI capabilities might follow that pattern.
And understanding that U-shape is crucial, right? Because if you only see the downward dip...
You might overreact. You might abandon a promising approach just because it hit a temporary valley. The real challenge is figuring out where that valley is, why it happens, and what pushes the curve back up again.
Yeah.
Is it just more parameters, more diverse data, a bigger context window?
Mapping the whole curve, not just the dip.
Precisely. And Anthropic actually leaned into this back in 2023 with their inverse scaling project.
Yeah, I remember that. They paid people to find tasks where models got worse as they got bigger.
Exactly. The goal wasn't to dunk on progress, but to proactively find these blind spots, these valleys in the scaling curve, so you could understand them better. This new research on test-time compute feels like a natural follow-up to that, broadening the search from just model size to reasoning length and mapping both the dips and the potential recoveries.
It's about charting the territory, weaknesses and all.
Right. The field is actively trying to map these complex dynamics now.
Okay, so this has been fascinating, but let's make it super practical. For the teams out there actually building and deploying LLMs, what's the actionable advice? Can we make a sort of checklist based on these findings?
I think we absolutely can, like a field guide for avoiding these pitfalls.
Okay, let's try. First up, prompt design. The pitfall is noise and distraction, right?
Right. So the fix is trim unnecessary context in your prompts. Maybe even use formatting, like bolding, to highlight the core task verbs and key information. Make the signal clearer than the noise.
Good one. Okay, next, few shot selection. We saw how models can fixate on bad heuristics.
Yeah, and if your examples only show weird edge cases, it can actually make that worse. So the fix. Start your few shot examples with clear prototypical cases. Introduce the edge cases later, if needed. Anchor the model first.
Anchor it. Okay. Then there's chain of thought visibility, the security risk.
Huge risk. Expose reasoning steps or attack vectors. The fix, especially in sensitive applications. Mask or even hash the internal reasoning steps. Only send the final, validated answer to the end user or the next system. Don't leak the process unnecessarily.
Makes sense. What about budget tuning? Letting models think forever is costly and risky.
Right. So implement adaptive stopping if you can.
Yeah.
Monitor that entropy gain or confidence. Yeah.
Mm.
And definitely set reasonable upper caps on token generation based on the task. Don't just leave it unlimited.
Control the compute. Then evaluation. How do we test for this?
The pitfall is only testing short reasoning paths. You'll miss the problems that show up later. So the fix. You have to evaluate your models across a range of reasoning lengths and compute budgets. Stress test them.
Don't just test the easy cases. Finally, model selection. Is newest always best?
Apparently not. The pitfall is assuming the latest, biggest model is automatically safer or better on your specific task under your specific conditions. The fix, actually compare Different model sizes, maybe older checkpoints versus newer ones, specifically on tasks prone to these inverse scaling issues before you deploy.
That's a great checklist.
And the key thing is, none of these require retraining a giant model from scratch.
Right, they're mostly about how you use the model.
Exactly. They're about treating compute budgets and reasoning paths as critical parameters to tune, just like you tune learning rates or batch sizes. They need to be first-class citizens in the MLOps pipeline.
Before we wrap up, just a quick thought on Grok 4, which just came out. These studies didn't test it, obviously.
No, too recent.
But the lessons seem applicable, wouldn't you say? If it exposes its chain of thought, watch out for prompt injection. If it does super long internal reasoning,
You might see some of these same failure modes. Distraction, fixation, maybe memory issues. It underscores the point. Bigger isn't automatically better, especially when the marketing hype gets ahead of the detailed, peer-reviewed analysis of these kinds of failure modes.
food for thought. Okay, so let's try and bring this all together. This has been a really deep dive. The big picture seems to be that the sheer power of AI scaling, it's undeniable. New models come out, benchmarks improve. That's real.
It is real progress.
But it comes with this hidden complexity debt. These studies, like Anthropic's apple counting or DeepMind security tests, they show that these incredibly advanced AIs can sometimes fail in ways that seem almost childishly simple.
Right. But the takeaway shouldn't be panic. It should be, I think, engineering sobriety.
Engineering sobriety, I like that.
Yeah. It means being deliberate. Control the context you feed the model. Hide the internal thinking when it's not needed for the user. Give clear examples in your prompts. And monitor the reasoning process, like a pilot checking instruments. Don't just let it run wild.
Be intentional about the thinking process.
Exactly. And there's a great line from Anthropic's paper that really sums it up. They say, high-capacity models remain promising, but naive scaling of test-time compute reinforces problematic strategies.
Naive scaling reinforces problematic strategies. That captures it perfectly.
It really does. It's a call for smarter scaling, not just bigger scaling.
So for you listening, maybe the takeaway is this. The next time you hear a vendor bragging about their new trillion-parameter model,
Ask some questions.
ask them about task-aware budgeting. Ask how they handle security when chain of thought is exposed. Ask them how they stop their models from overthinking simple problems.
Because models that just think too much without direction, that's probably not the future we're aiming for.
Right. Thought is valuable, but controlled, focused thought is what's truly productive if we can achieve that control.
Then AI scaling really can be that amazing force multiplier we hope for.
But without it,
Without it, we risk building incredibly bright models that just keep getting stuck, trying to prove that one apple plus one orange somehow equals 3. We end up in that degenerative spiral instead of multiplying our capabilities.